Okay, so this problem is going to be a lot like what we did in the section where we were computing the gravitational field inside of a shell of mass. Remember how we had this one where you have this shell of mass where it's hollow on the inside, but it's a sort of a spherical shell, and we ended up concluding that the gravitational field on the inside is actually zero. You remember that example? That was one of the examples from in the section. I mean, you can look back through the section and find that. Yeah. We're going to make a very similar argument here. It's just that some of the details are going to end up being a little bit different. So we're going to start off using the hint. It says you may assume, it even makes a reference to the example 645. You may assume that the vector field is spherically symmetric. So in particular then, this gravitational field is going to be some function of radius, some function of distance from the origin. I don't know what that function is. This is a big question mark as to what that is. But it's going to depend on your radial distance from the origin and then times your position vector. So in other words, let me draw a picture here. Here's our gas cloud. And it's the solid, it's gas, right? But it's a solid ball of gas. And wherever you might happen to be inside of there, the gravitational field is going to point radially with a magnitude that depends only on the distance from the origin. Does that seem kind of plausible? And we can make a symmetry argument like we did earlier with magnetic fields, namely, when you take some physical thing, if when you rotate it, if it doesn't change, right? This is a solid ball. Balls have all sorts of symmetries. Then, if nothing's changing, then of course the gravitational field doesn't change. But furthermore, when you rotate something, the gravitational field has to kind of rotate along with it. And so, if the item is symmetric, then the gravitational field has to be correspondingly symmetric. That's kind of the idea behind this assertion here. You may assume that this vector field is spherically symmetric, which gives us this. Is everybody okay with that argument? Okay. All right, anyway, it's a given for the problem. That's kind of convenient. So the problem then says, let's compute the flux through a sphere of radius rho, and it observes that we're going to consider only the gas inside that sphere. Fine, so let's do this. Here's a point that we're interested in that's sitting inside of this gas, and we're going to look at this sphere of radius rho, so whatever that distance is, rho. So we're going to compute the flux through that sphere. Okay, and we're going to do this two different ways, as is very often the case. Very often in math and physics problems, it's like I like to call them bank shots, and this is going to be a kind of a mathematical bank shot. We're going to compute the gravitational field first by computing flux. Okay, so here we go. Let's call this, by the way, let's inside there, we'll call that, let's see, this is, we haven't used any names yet. Let's say that this surface, that surface there we'll call S, and the solid on the inside we'll call B for ball. How about that? Okay. All right, so we would like to compute the gravitational flux through that surface. That is the surface integral over S, gravitational field dot ds. And I'm going to compute this two different ways. So first observation, I know how to compute gravitational flux. We have a handy-dandy formula. The gravitational flux can be computed from mass density. And that is, there you go, gravitational flux, negative 4 pi gm, right? And that just comes out of the fact that we know that the divergence of the gravitational field is mass density. Do you remember that one?
Yeah, but I got
you got some questions about that as well?
Yeah, but like after this.
Okay, yeah, we'll talk about that. So let's just use this theorem here for the moment, and we'll talk about that later. Okay, so going back to, let me just put that here. Gravitational flux, as per the formula, negative 4 pi G M. Now, what is our mass? Well, the mass, let's see, we've got the constant density of delta, and we've got a sphere of radius rho, so we're going to have density times volume, which is 4/3 pi rho cubed. Cool? So this is M. Okay, so that's one calculation. Now another thing we can do is we can compute this flux a little bit more directly just by the fact that we have kind of a formula for this gravitational field. Namely, the gravitational field is, well, it's some function depending on rho times the position vector x. That's what that is. Now, what about this ds? Well, the ds, I'm going to rewrite that as unit normal vector ds scalar. And that I can actually plug in for. Oh, sorry, I forgot my dot there. Shame on me. What's this unit normal vector? Well, again, sphere centered at the origin. We love spheres centered at the origin. The unit normal vector is easy to write down. It's just x divided by the length of x. Excuse me. Or said differently, x divided by the radius, and the radius is rho. So I claim that this unit normal vector for that sphere, because it's a sphere centered at the origin, this is x divided by rho. Is that okay? Okay. ds scalar. So altogether, x dot x, of course, is length squared. Length is rho. So I have length squared divided by length. So I have f of rho times rho ds. This is all constant. And since that's a constant, I can factor it outside. That gives me, so rho f of rho. And then just the surface area of the sphere, which is 4 pi rho squared. Is that cool? Okay. All right. So altogether, we have, let's see here. Let's group these terms. This is f of rho times 4 pi rho cubed. Okay. So now, again, we've computed the same thing in two different ways. On the one hand, we computed it using effectively Gauss's divergence theorem. On the other hand, this gravitational flux we computed by brute force, just chapter 5 techniques. I wrote down what I know about the field. I rewrite the vector differential and just brute force calculate it. Right? And so having computed the same thing two different ways, these two things must be equal to each other. This is our mathematical bank shot. And therefore, those two things are equal. Oh, I didn't, sorry. Yeah. So therefore, those two things are equal, and then I can just solve for f of rho. And let's see here. When we solve for f of rho, see that rho cubed is going to cancel with that rho cubed. That pi is going to cancel with that pi. That 4 cancels with that 4. And altogether, I get just f of rho equals negative 4 pi g delta over 3. I'm sorry. Yeah. Is that cool? And so that's what we needed to know. We needed to know what was this mysterious f of rho that I have to multiply by x in order to get the actual gravitational field. So we're done now. The gravitational field is all this business, which, by the way, note it's a constant. It's kind of interesting how it's everything, that all the rho's canceled. This is a constant. It's negative 4/3 pi g rho x. So there is your actual gravitational field. inside of that ball. And one thing that's kind of cool about this, I've always thought this was really neato how this works. Now, you'll notice I made this a cloud of gas, just because it's kind of weird to imagine yourself inside of a solid. Like if I were to say, hey, suppose you were, halfway to the center of the Earth. Well, you'd be crushed, right? It's solid down there. You can't get there. But if you visualize a cloud of gas, you can kind of have an intuition about actually maybe, taking a rocket ship or something through that cloud of gas. But this, you could totally change the problem and say, well, let's pretend it wasn't a cloud of gas. Let's pretend this was the solid, let's say, Earth. It's still roughly constant mass density. It's not exactly, but it's, not far off. And what this says is that the gravitational field, here's a formula for it, and in fact, then the length of the gravitational field, if you wanted to compute the length of the gravitational field, well, it's going to be a bunch of constants. I'm sorry, this was a delta. Shame on me. I'm sorry, I miscopied. That's a delta. There we go. Sorry about that. And then, delta. And then in computing the length of the gravitational field, the length of x is rho. So what this says, this is really interesting. It says that the length of the gravitational field is proportional to how far you are away from the origin. In other words, how far you are away from the center. So when you're at the center of the Earth, there is no gravitational field there. If you're halfway toward the edge, you have half as much gravitational field. If you're 90% of the way toward the edge, still inside the solid Earth, then you have 90% of the gravitational field. It's a linear relationship on distance from the center of the Earth. And I think that's kind of cool. Yeah. Anyway, so. Does that make sense to everybody? Any questions? Alrighty. So do notice, I think it's very worth noticing that what we did here, namely computing the flux once with Gauss's divergence theorem, once by brute force, equating the two things, solving for f of rho, and then drawing our desired conclusion. That's exactly what we did in this example here, where we have the large hollow spherical shell of uniform mass density. The picture of which is here. Here's the shell, but it's empty on the inside, and the question that we dealt with was, well, what can I conclude about the gravitational field at a point like that? And notice what we did is, on the one hand, we wrote down the spherically symmetric gravitational field. We computed the flux brute force. Then we computed the flux using Gauss's divergence theorem. Well, there's no mass on the inside, so therefore the flux is zero just by the Gauss's divergence theorem and gravitational flux. And so therefore that ended up being equal to that, which allows you to conclude that f of rho is zero. And once you have f of rho, then you know the gravitational field. So same pattern there as in this example. So I'm going to encourage you to read this example again and note that what we did in this homework exercise is very, very similar, just different details. In this problem, there is no mass on the inside. In the problem that we just worked here, there is. It's a solid, constant density mass on the inside. And that's the only difference between these two problems. Does that make sense?